अच्छा, so we were talking about catalyst, or उसके अंदर we were talking about that they reduce activation energy, or we were also discussing heterogeneous catalyst where there was adsorption and deadsorption. And I'm also going to revise another type of catalyst, which is a homogeneous catalyst. A homogeneous catalyst, homogeneous catalyst. So it is a type of catalyst which has the same state as the reactants. Okay, so let's discuss. There's one example that needs to be learned. They have catalyst as the same state as the reactant. Same state as the reactant. And the other, so the example for this was that there was a reaction in which, so quickly doing the example, you have this reaction 2i minus 1, and you have another reaction which is S2O8 2 minus 2 minus plus 2 electrons, and it's in equilibrium with 2SO4. 2SO4 2 minus. This is 0.54 volts. This one. So this is 0.54 volts. This one is 2.01 volts. So this one, higher potential gains electrons, lower potential loses electrons, and at the end of the day, you had this reaction, which was that the reactants are I minus 1 and S2O8 2 minus 1. So it was 2I minus 1 plus S2O8 2 minus, and the products were iodine plus 2SO4 2 minus. Okay, so in the first reaction, the reactant is 2I minus 1. In the second one, the reactant is S2O8 2 minus. And the product in the first one is I2, and the product in the second one is 2SO4 minus 2. So you have this reaction. And when we were discussing this reaction, we said that in this reaction, the activation energy is very high. Why was it high? Because uh, the reaction would not happen, or it would be very slow, because both ions were negative. Okay, so both ions were negatively charged, and therefore the reaction had very high activation energy, and it was a very slow reaction. So instead, what you do is that these two equations are not going to react with each other, because both ions are negatively charged. They're going to repel each other, and they're not going to meet each other because of repulsion. So this reaction is not going to happen. So to make this reaction happen, okay, this is not going to happen. So to make this reaction happen, you add a catalyst, which is, so the catalyst is Fe3 plus or Fe2 plus. And the value for that, for the E naught for that is 0.77 volts. Now, since these two are not reacting with each other, because the end result is they both have negative ions and they repel each other, so they're not going to react with each other. The first one is not going to react with the third one. So they start reacting with iron catalyst. Iron is the higher potential, so it's the one that's going to gain electrons. And iodine is the lower potential, so that's the one that's going to lose electrons. So you're going to have a reaction, and that reaction, so the first and the second equation, they're going to have a reaction. You add up the reactants and the products. The first one, the reactant is over here. The reactant is 2I minus 1. And in the second one, the reactant is 2Fe3 plus. And the products in the first one, I2 is being formed. In the second one, the product that's formed is 2Fe plus 2. So this is step 1. This is the first reaction that's happening. Okay, this is step 1. And then the same iron catalyst would also react with the SO4 equation, SO4 is this one is the higher potential equation, so it's going to gain electrons, whereas the Fe equation, because it's relatively the lower potential, it's going to lose electrons. So the same iron catalyst reacts with iodine, comes up with this reaction, and the same iron catalyst reacts with the sulfate equation, and you're going to get step 2, which is if you add up the reactants are 2Fe2 plus, and and the reactant over here is S2O8 minus. S2O8 minus 2, and the products are over here. The product is 2Fe plus 3, and in the second one, the product is 2SO4 minus 2. Anyway, so you get this is your step 2. So I'm going to just quickly recap. I'm going to recap that I was trying to react iodine with S2O8, and I was supposed to get this reaction, but this reaction is very, very slow. Okay, this is just an example of homogeneous catalyst. So the reaction was very slow because both ions turned out to be negative ions, and negative ions don't attract each other. They're not going to collide with each other. So the reaction, they're never going to meet, or it's going to be very difficult for them to meet. So the reaction is not really going to happen. So to make this reaction happen, I added this iron catalyst, and what this iron catalyst did was that it started reacting with the iodine equation, gave you this reaction. This equation also reacted with the sulfate S2O8 equation, and it gave you this reaction. So the whole reaction over here was broken down because of the iron catalyst into 2 steps. And you're getting both products. I minus 1 is changing into I2, and S2O8 minus 2 is changing into SO4 minus 2. This is what your reaction was doing. I minus 1 was changing into I2, S2O8 was changing into SO4 minus 2. The only difference is your reaction was doing this in 1 step, whereas by adding the catalyst, the reaction is happening now in 2 steps. And these 2 steps are a lot faster. Why are they faster? Because if you look at the reactants, now in both steps, the reactants are oppositely charged ions. So they're both oppositely charged ions. Uh, so more frequent collisions are obviously going to happen because they're going to attract each other. So you're going to get a lot more frequent collisions because they're going to attract each other, and they're going to collide with each other. So step 1 is going to happen at a very fast rate. The step 2 is also going to happen at a very fast step. Uh, this is going to be the overall reaction. If you try to do this directly, is not going to happen, or it's going to happen at a very slow rate, or it's going to have a very high activation energy. Okay? So you have to remember, for homogeneous catalyst, you have to remember this example, this entire example in all its details. ठीक है, Burera, Sara, is this clear? Akib, did you get this?
Yes.
Yes, sir.
Achha, so we were discussing catalyst. Coming back, we actually did this. We were discussing catalyst. Okay, catalyst reduces activation energy, and we talked about yesterday. We talked about heterogeneous catalyst. That if it's the catalyst in which the catalyst has a different state compared to the reactants. So uske अंदर I had explained that how does it act and why are transition metals very good catalysts, because I explained that they have a weak tendency to attract electrons. So if you have a transition metal and there's a triple bond, the triple bond electrons over here in the middle, they're going to get attracted by the iron catalyst very weakly. And what would that do? It would break the bond. Okay, that was the thing that was stopping the reaction from happening. That the triple bond was so strong that it was very hard to break. But by adding a catalyst, you were able to do that. So there was a process of adsorption and deadsorption, that even these weak bonds are eventually going to break, and nitrogen would then make new bonds with hydrogen or with any other thing. So, so this is how heterogeneous catalysts work. Okay, so you must know how these catalysts work. Another thing about rate of reaction that has to be remembered from AS is that's about biological catalyst. Okay, which are which are enzymes. So, what are biological catalysts? Now, these are your enzymes. And enzymes work on a substrate. Okay, they attack a substrate. The only thing, you don't need to go into a lot of detail. You probably take biology, so you probably know a lot more detail. But your knowledge of biological catalysts and enzymes and substrate, it's eighth standard knowledge that is required, which is the lock and key model. So we're going to work on a lock and key model, which is that enzymes are very shape specific. And it's not just enzymes, it's actually all biological substances. They are very, very shape specific because they all have a specific shape. ठीक है मतलब for example if you look at your hand has five fingers ठीक है so it has a very specific shape and because of that shape the function of your hand your hand is going to function in a particular way uh, and that is also true at the cellular level at the smallest scale as well. So if a molecule has a very specific shape and I'm going to draw the shape of a molecule, let's say this is the molecule. Let's say this is the molecule. Now, this molecule is going to react with any enzyme that actually matches, and this is going to be called your substrate. And it's going to match with exactly a complementary substance or a molecule, which is your enzyme, which whose groups, not only the shape, but also the groups or in the active site, they match. Hopefully, this is. So here's your enzyme, and that's your substrate. Okay, so it's a basic lock and key model. Hopefully they fit. I said not only are the shapes going to match and they're going to fit with each other, uh, but the groups and the active sites they should also match. And biological molecules are very large and very complicated. Okay, if you look at a red blood cell is a combination of many different uh, tertiary proteins, and that combine to form a red blood cell. If it's going to capture oxygen or attract oxygen molecules, it has a very specific shape for doing that. So enzymes are very large molecules, but the oxygen molecule is not going to get attracted to any place. It has a very specific active site where it attaches. So enzymes have a shape specific active site which binds to a substrate having a complementary shape. So having a complementary shape forming an enzyme substrate complex. Okay, so the picture that you see in front of you, I mean, you had an enzyme, you had a substrate, they were shape specific, they ended up matching, the groups are going to interact with each other and they're going to have a reaction. And as a result of the reaction, the substrate would change. Okay, we don't know how it's going to change. Every reaction is different, but it might break into two pieces. Okay, so the substrate breaks and the reaction happens and it breaks down into two pieces. So the only thing that you need to know about biological catalyst enzymes are that they're very shape specific. There's a lock and key model, which is that if an enzyme has an active site and the active site has a very specific shape, the substrate is going to have a complementary shape to it, and only then would it interact with the enzyme. Okay, its active site must exactly match with the active site of the substrate, and only then would they form an enzyme substrate complex, which would lead to a chemical reaction. Uh, so your whole biological processes that depend on shapes. ठीक है, is this clear? Ali, is this clear? Akib, clear?
Yes, sir.
अच्छा, so we did. This is all about catalyst. Another thing about AS that has to be known is your Boltzmann distribution. ठीक है, before moving to A2 reaction kinetics, the Boltzmann distribution. What is the Boltzmann distribution? It's the distribution of particles, or it's the energy distribution of particles. Now, with distribution of particles. Now, whenever you see particles, whether it's a liquid or a gas or a solid, particles don't have exactly the same energy. Okay, particles are all continuously bumping into each other. Some are gaining energy, some are losing energy. So, so in AS, you study that these are your energies. Okay, particles can have any energy. So if you're in a room, there's gas in a room, or there's air in the room. So the particles of air, okay, there are lots and lots of particles in air. Some are less energetic, some are very energetic. Okay, some, so the energies are distributed, but not equally because they're bumping into each other. Some are gaining energy, some are losing energy. So this is the energy axis. This is the proportion or number of particles on this axis. And usually the graph is slightly skewed to the right. What this means is that if your room is at 25 degrees centigrade, that means most particles have energy, uh, and we're talking about the kinetic energy. And remember, kinetic energy is proportional to the temperature. If you have a higher temperature, you have more kinetic energy. So if your room is at 25 degrees centigrade, then most particles would have energies that would be very close to 25 degrees centigrade. So the number of particles when you have average energy, okay, this peak represents average energy of the particles, or the middle part. So this is the energy that most of the particles are going to have. So the height represents the number of particles. So most of the particles are going to be having energy values that would be very close to the average energy. So if your room is at 25 degrees centigrade, there would be a few particles at 27, there would be a few particles at 23. There would be, so most of the particles would be having energies around the average kinetic energy. Particles having very low energy, there would be very few. So low energy particles, there would be hardly any. Like if you're in a room and you expect that some air particles would have energy values that would be very close to minus 20 degrees centigrade, then the number would be very, very few. And the same is true that high energy particles, their peak would be lesser as well. Okay, so if you expect that particles in your room, uh, if you try to count the particles having very high energy, then there would be very few. Most of the particles are going to have average energy. So the graph would be higher in the middle and lower on the sides. Okay. Sara, is this clear? Abu Raya, clear? Mahfuz?
Yes, sir.
Yes, sir.
अच्छा अब इसमें there's another thing which is कि what happens when you increase or decrease temperature. What happens is if you increase temperature, the number of high energy particles increases. So the graph is going to rise from here because you're now at a higher temperature. So there would be more particles at higher energy, and there would be even fewer particles at lower energy. That if you turn on a heater in a room, then the number of particles having high energy, that's going to be greater. So the graph gets even more shifted to the right. So this is your higher temperature graph. And vice versa, if you decrease temperature, then that means because you have decreased temperature, the low energy particles would be a lot more now. So the graph is going to rise over here, the number of particles are going to be more over here, and the number of high energy particles would be lesser. So the graph would actually get even lower on the right side. So this is so this is how the graph would look for lower temperature. So what we can say is that at lower temperature it shifts to the left and rises. It becomes higher because the particles are now distributed. If at a lower temperature, the particles are now distributed at fewer energy levels. So the number of particles, the number of particles stays the same, but now they are more concentrated at a few energy levels. At higher temperature, the particles get distributed at a very large range of energies. So shifts to the left and rises. और दूसरे केस में it shifts to the right and its peak decreases. It becomes lower. ठीक है, क्योंकि the particles that were at average energy, they're going to shift. तो यहाँ पे energy कम हो जाएगी, so this peak would be lesser, and it's going to shift because more particles are present at higher energy. So that's a Boltzmann distribution. Achha, what other thing can you guess from a Boltzmann distribution that you might be asked to show the presence of a catalyst. So catalyst is your activation energy. So this is your catalyst. This is the minimum energy that is needed to start the reaction. So all these particles that have energy, this acts as energy. So all the particles that have energy that is lesser than the activation energy, they're not going to take part in the reaction. They're going to collide, but they're not going to. It would not lead to a successful collision because they don't have enough energy. So particles with less energy, they won't be able to break their bonds and form new bonds. But particles having energy that is greater than the activation energy, those are the ones that are going to take part in the reaction. So for example, if you look at the red graph, all these particles over here, these high energy particles, they are the ones that are going to successfully collide. Okay, so I'm only focusing on this. So particles having energy greater than EA, so greater than EA are the ones ये इसको simply लिख दो कि they are the ones that are involved in successful collisions. ठीक है, they are the ones that are actually taking part in the reaction. ठीक है, the rest of them are just colliding, but they're not. It does not lead to successful collision. Why does increasing temperature actually increase the rate of the reaction? The reason it increases the rate of the reaction is that now even more particles are present at higher energy. ठीक है, so at higher temperatures, you have more particles having energy greater than EA. As a greater than EA. So that would lead to a faster reaction. More successful collisions would happen. ठीक है, Ali, आगे business clear? Abu Rara, is this clear?
Yes, sir.
Yes, sir.
So you get even more successful. You get even more successful collisions. So this is all you're going to be asked. Okay, that's the only thing. I mean, you have all those factors, temperature and pressure factors. But remember, okay, the only thing that you can actually observe, that's temperature changes on the Boltzmann distribution, and the other thing is you can observe the what a catalyst does. And remember, I haven't added a catalyst yet. I was just talking about activation energy. What would happen if I add a catalyst? If I add a catalyst, the same thing would happen. The activation energy is going to be lower. Okay, so this is your EA, which is catalyzed for a catalyzed reaction with a catalyst. So EA decreases, it decreases activation energy. And when it decreases activation energy, even more particles are now able to take part in the reaction because they have energy that is greater than the activation energy. So you can see what a catalyst does on a Boltzmann distribution, and you can see what temperature does in a Boltzmann distribution. ठीक है, बाकी factors you won't be able to judge from a Boltzmann distribution, like pressure changes. ठीक है, like क्योंकि pressure is a factor जिसके ऊपर rate depend करता है. You can't really determine what would happen if surface area changes. ठीक है, the Boltzmann distribution ये याद रखना, बल्कि I'm going to write it down. कि the distribution, the observable changes are when you change temperature or you add a catalyst. ठीक है, Boltzmann distribution deals with these two things. Otherwise, Boltzmann distribution के अंदर there's not going to be much of a difference. Pressure change करने से, concentration change करने से. चलिए, now what we're going to do is we're going to focus on rate of reaction, जो हम पहले कर रहे थे. अच्छा, so you have a reaction that's going on. There's H2 and there is Cl2, and they're reacting to produce HCl, two molecules of HCl. अच्छा, इससे आगे जो भी whatever we're going to study, we're going to mainly talk about the relationship of rate with concentration. ठीक है, this is the only thing that we're going to talk about. There's going to be an order of a reaction, वो भी हम discuss करेंगे. But we are only interested in the relationship of the concentration of the reactant. Product concentration usually doesn't matter. Sometimes it does matter as well. So I'm going to just write down product concentration. Bracket में लिख देते हैं product concentration usually doesn't matter because the product is not doing anything in the reaction. But why is HCl being formed? Because H2 particles and Cl2 particles are bumping into each other. ठीक है, ये यहाँ से आ रहे हैं, ये यहाँ से आ रहे हैं, and they collide with each other. So it all depends on the concentration of these reactants. अगर ज़्यादा reactants होंगे H2 के and more concentrated, then obviously they're going to collide with each other with a higher frequency, and they're going to bump into each other more, and the amount of HCl is going to be produced at a faster rate. Vice versa, अगर concentration कम होगी, so it all depends on the reactant, ठीक है, not really on the product. We don't really care कि HCl ज़्यादा है कम है. The rate of the reaction or the speed of the reaction would depend कि how many collisions are happening between these two. So product concentration usually doesn't matter. It actually does matter, but in a very few cases. So let me write the exception, except in autocatalyzed reaction. So in autocatalyzed reactions, what are autocatalyzed reactions? Where the product that is formed acts as a catalyst. Which means that as soon as the product is formed, catalysis starts. ठीक है, because the product itself acts as a catalyst. As an example, you have A plus B are reacting to produce C. So initially, the reaction is going to be very slow. ठीक है, initially it's going to be slow. But as soon as C is formed, the reaction would speed up. And it's going to speed up. Obviously, reactants, they get used up, the reaction would slow down again. तो ये सारा मैं यहाँ पे पहले लिख दूँ कि right in the beginning, ये let's say मैंने ना reactant की concentration plot की हुई है, ठीक है? I've plotted the reactant concentration. So start में you have a very high concentration of the reactants A and B, but the reaction is very slow because there is no catalyst. Catalyst is the product. Product बनेगा तो catalyst मतलब C would come in, ठीक है? So initially the reaction is very slow because there is no C. When they react slowly, so the reaction is slow, all of a sudden C is formed, and when C is formed, the reaction kind of speeds up. Or eventually every reaction has to slow down again and go to zero. Why? Because you run out of A and B. So start के अंदर you have no catalyst. Middle part, the product all of a sudden forms. Forms and catalyzes, starts catalysis. और फिर बाद में you run out of reactants. ठीक है सारा, is this clear, Akib? Abu Rera, clear है?
Yes, sir.
Yes, sir.
Okay, so the point is that auto-catalyzed reactions can come in your exam as well, but usually reactions are not auto-catalyzed, okay? And product concentration usually doesn't matter. तो इसलिए I've so ये बस यहाँ पे ख़त्म कर देंगे. अब हम assume करेंगे the product concentration doesn't really matter, ठीक है? It's only the reactants that are taking part in the reaction. So the relationship over here is going to be that the rate of the reaction would depend on the concentration of H2 and the concentration of Cl2. Now, the rate of the reaction would depend on the concentration of both the reactants, H2 and Cl2. If H2 is higher, there's going to be more collisions. If Cl2 is higher, there's going to be more collisions. But we don't know the order of the reaction, A and B. What does A and B represent? That's the first thing. Okay, so let's discuss, and let me write the definition of what A is. A or B are known as the order of the reaction. I said, what does that stand for? Okay, what's the technical definition? Because if it's coming in your paper, you have to define it properly. So it's the exponent of the concentration of a reactant in a rate equation. Okay, so it's the exponent of the concentration of a reactant, but it's basically the power. I said, what does it stand for? What does it mean? First one, we're going to talk about order 0. That's the first one. So if we talk about order 0, ठीक है, just wait 1 minute, ये जान के बाद हम continue करते हैं, ठीक है? अच्छा चलें, let's start with order 0. ये बस order 0 पहले introduce कर लें कि what is order 0? कि I said that rate depends on the reactant concentration. But the power is 0. What that means is, now in any reaction, okay, if I draw a graph, the reactant concentration is going to decrease. But how is it going to decrease? In order 0, it's going to decrease. Okay, this is your reactant concentration, and this is your time, and the gradient. ठीक है, remember ये हमने first discuss किया था कि the gradient is always the rate. अच्छा, the gradient is going to be constant. पहले तो order 0 explain कर लें. Order 0 का मतलब है the rate of the reaction does not depend on the reactant concentration. 0, if you put any concentration over here, any value over here to the power 0 would come out to be 1. So it doesn't really matter what the reactant concentration is. The rate value would still be the same. So order 0 indicates that rate does not depend on the reactant concentration. ठीक है, so it's not dependent on the reactant. कि अगर आप reactant ज़्यादा डालो कम डालो, it has no effect on the speed of the reaction. So what happens is, अच्छा, usually you don't, normally in real life you don't get these graphs like these, because अगर आपने, if you have done any reaction, ठीक है, like if you put a Pepsi in a glass, start के अंदर there would be a lot of bubbles. So the reaction is going to be faster at the beginning and it's going to slow down at the end. Most of the graphs are going to look like that. So usually rate of reaction depends on the reactant concentration. But sometimes, and we're going to discuss in detail why sometimes जब हम mechanism पढ़ेंगे, why sometimes it doesn't depend on the reactant concentration. So उसके अंदर क्या होगा कि reaction, if it's decreasing at the start at a particular speed, end तक वो उसी speed से decrease हो रहा होगा. ठीक है? So it's like if you look at a glass of Pepsi and there are bubbles forming at the start, so even after 10 minutes, the bubbles are forming at the same exact speed, and which means that the reactant concentration doesn't matter. Okay, time goes there, reactants come again, but nothing is happening to the speed of the reaction. So that's order 0, and sometimes, usually not. Okay, usually this is not observable. In the real world, you don't see this happening. Usually, what happens is, even if you're burning wood, the start में wood is burning at a very fast speed, ठीक है, and then slowly the flames die out, and then क्यों die out हो रहे हैं? Because the reactant is getting used up, and slowly उसके flames कम होते जाएंगे और फिर the flames are going to die out. So any reaction usually is fast at the beginning and slower at the end. But in order 0 reaction, it would maintain speed. उसके लिए reactant doesn't really matter. Reactant ज़्यादा है, कम होते जा रहे हैं, but the reaction speed remains exactly the same. So that's order 0. ठीक है, order 0 clear है? Sara, is this clear? Abu Rera, Mahfouz, is this clear?
Yes, sir.
So Akib,
Yes, sir.
चलो ठीक है. So this is order 0. और इसमें there's a concept which is half life. ठीक है, half life is कि how much time does it take for the concentration to decrease by half? So it's this time, right? कि मतलब the concentration was initially over here, तो half तक आने में it took this much time. अच्छा, then what's the second half life? How much time it takes for the concentration to decrease by half again? So now your half is over here. So then again, third half life would be again how much time it takes for the concentration to decrease by half. Then again, how much time? So what's happening is that the time required keeps on becoming smaller and smaller. ठीक है, that's your half life. So इसके अंदर what we can say is कि the half life, each half life is half of the previous half life. Half of the. So that's the first way. If you do an experiment and you plot the concentration of a reactant and you get a straight line, which means, but if you're getting a straight line, that automatically means it's order 0. You don't even need to calculate half lives, okay? But each half life is half of the previous half life. चलिए ठीक है, we're going to continue with this in the next class, ठीक है, inshallah. Okay then. Quick question is Pusho. Otherwise, you're allowed to leave the class. Okay.
Okay, sir. Okay, Allah Hafiz.
Okay, love.